unpack this. For literally thousands of years, the basic idea about space was that it was just empty. Nothing.
Right. You had thinkers like Aristotle with his horror vacuuming. The idea that nature just abhors a vacuum.
And that idea really stuck even in the 17th century when Otto von Guericke did his big demonstration with the Magdeburg hemispheres. He was just proving the absence of air.
Exactly. Not the absence of, existence itself, but that whole concept of a cold, absolute void has been just completely dismantled by modern physics.
And that transition from an empty space to a full vacuum is, it's one of the biggest shifts in thinking in all of science.
It really is.
Our sources today, they range from the foundational work on fields by Maxwell all the way up to quantum field theory and general relativity. And they all point to the same conclusion. Space is not silent. It's an active, multi-layered medium.
Absolutely. So the mission for this deep dive is to figure out what's left when you take everything away. If you could hypothetically strip out every planet, every star, every single atom, what's still there? What's the fundamental architecture?
So we're starting with the nothing that is actually a something. It sounds like a paradox, but this is real physics. So where do we start? What's the one thing you can absolutely never remove?
We have to start with the quantum vacuum. In classical physics, a vacuum means zero energy, period.
But not in quantum mechanics.
No, because the Heisenberg uncertainty principle just forbids it. If you had zero energy, you'd know the exact position momentum of every particle, and that's just not allowed.
Okay, so instead of zero, you have something called 0-point energy. And that leads to what exactly?
It leads to a vacuum that's this restless, bubbling sea of energy. It's full of what we call virtual particles, these antiparticle pairs that just pop into existence for a fraction of a second.
Borrowing energy from the vacuum.
And then they annihilate each other and vanish before anyone notices the debt.
That sounds like something you'd see on a blackboard. Pure theory. But how do we know this quantum foam is actually real, that it affects our world?
Because it creates a measurable force. The classic proof is the Casimir effect. You take two perfectly flat, uncharged metal plates in a vacuum, and you bring them incredibly close together.
Okay.
Now, outside the plates, the virtual particles can fluctuate in any wavelength they want. But the tiny gap between the plates restricts them. Only certain wavelengths can physically fit in that space.
It's like a guitar string, right? You can only get certain notes, certain standing waves.
Exactly. It's the perfect analogy. And because there are fewer possible fluctuations between the plates than outside, you get an imbalance in vacuum pressure.
And that pushes them together.
It pushes them together. A real, measurable, attractive force generated by nothing but the vacuum itself.
And it's not just big forces, it affects the atoms themselves.
It does. Look at the Lamb shift in a hydrogen atom. Theory said two of its energy levels should be identical, but they're not. There's a tiny, tiny difference.
And that difference is because of the quantum foam.
Yes. The electron is constantly interacting with these virtual particles, causing it to sort of jiggle in its orbit. That jiggle shifts its energy just enough to be measured. The vacuum is fundamentally changing the structure of the simplest atom.
That is it's hard to overstate how profound that is.
And it's foundational for technology. The mechanisms behind carbon-14 dating, even how lasers work, they depend on these fluctuations being real. The vacuum is an active ingredient in the universe.
Okay, so beyond energy fluctuations, there's another field in the vacuum that's responsible for one of the most basic properties of matter itself, mass.
You're talking about the Higgs field. And just like the quantum vacuum, this field permeates all of space and all of time. The key is that it has a non-zero value. It's always on.
So for anyone listening, what's the best way to picture how this field gives a particle mass? Because it's not something the particle just has on its own, right?
Right. The best analogy is to think of it like walking through deep snow. The snow is the Higgs field. If you're a photon, you just glide right over the top, totally unhindered. You travel at the speed of light. You have no mass.
But if you're, say, an electron?
If you're an electron or a quark, you sink in. You have to push through the snow. You interact with the field. You drag against it.
And that resistance, that drag, that's what we perceive as mass.
Precisely. The stronger the interaction, the more mass a particle has.
Yeah.
And that energy, that mass, is effectively being drawn right out of the vacuum itself.
And the last piece of this fundamental fabric is space itself. It has a shape.
That's general relativity, Einstein's metric field. Space isn't a rigid stage, it's a dynamic geometric thing. Even in a total void, space has a curvature that tells things how to move.
And the proof that it's dynamic is gravitational waves.
Exactly. ripples in space-time itself. They travel at the speed of light, and they don't need any medium to travel through because they are the medium. The fact that space can ripple and wave proves it's a physical substance.
So this is where it gets really interesting. We started by taking everything away, and already we've got quantum foam, a mass-giving field, and a geometry that can carry waves.
That's the baseline. That's the stage. Now let's start adding back the actual stuff. The visible fog of gas and plasma that makes up all the atoms.
And we can start right here in our own galaxy with the interstellar medium, the ISM, the gas and dust floating between the stars. It's what, maybe 10 to 15% of the galaxy's normal matter?
That's right. And it's almost all hydrogen and helium. But you called it a fog, and that's a great way to put it because it's not uniform at all. It's this chaotic, multi-phase environment.
So give us the extremes. What's the coldest, densest part of the ISM look like?
That would be the molecular clouds. These are the star nurseries. They're incredibly cold, just 10 Kelvin, and their density gets up to around 1,000,000 particles per cubic centimeter.
Which sounds dense, but in cosmic terms, it's still practically nothing.
Oh, absolutely. To put that in perspective, 1,000,000 particles per cubic centimeter is still 1,000,000,000,000 times less dense than the air you're breathing right now.
1,000,000,000,000. Wow. Okay. And what about the other end of the scale? The hottest stuff.
That's the hot ionized medium, or HIM. This is plasma that's been superheated by supernova explosions to millions of degrees Kelvin.
So the explosions blow these huge bubbles of super hot, really thin gas.
Exactly. So you have these cold, dense clumps sitting inside these vast, hot, empty bubbles, all in the same galaxy.
Okay, so that's inside our galaxy. What about the truly vast space between galaxies? The intergalactic medium, or IGM?
The IGM is even more rarefied. We're talking maybe 1 to 100 particles per cubic meter. It is an incredible vacuum, but, and this is crucial, we now know that's where most of the universe's normal matter is hiding.
This is the missing matter problem, right? We could calculate how much matter should have been made in the Big Bang, but when we counted up the stars and gas in galaxies, it didn't add up.
Right, we were short by a huge amount. We could only count for maybe 9% of it inside galaxies. But very recent research in 2025, using fast radio bursts, or FRBs, finally found it.
And the answer is?
About 76% of all the normal baryonic matter in the universe is in the IGM.
How can a split-second radio flash tell you that?
It's ingenious. As that FRB signal travels across the cosmos, it passes through the plasma of the IGM. The free electrons in that plasma slow down the lower frequency radio waves just a tiny bit more than the higher frequency ones.
So the signal gets smeared out over time.
It gets dispersed. And the amount of that dispersion tells you exactly how many electrons it passed through on its journey. It lets you weigh the universe.
And that missing matter is mostly found in the cosmic web structure.
Exactly. The IGM isn't uniform. It's arranged in these massive filaments connecting galaxy clusters. And that's where we find the WH, the warm-hot intergalactic medium.
The WHM. It was so hard to find because it was in that awkward temperature range, too hot to see easily, but not hot enough to glow brightly in X-rays.
That's right, between 100,000 and 10 million Kelvin. The hydrogen is completely ionized, so it's invisible to most telescopes. We had to find it by looking for traces of highly ionized oxygen by using those FRB dispersion measures.
So the biggest vacuum holds the most stuff. Another paradox.
The universe is full of them.
Okay, so we have the gas and plasma. Now, for something that's only about 1% of the ISM by mass, but is, I guess, disproportionately important, cosmic dust.
Cosmic dust is the absolute unsung hero of cosmic chemistry. We're talking tiny grains, smaller than a micrometer, made of things like silicates and carbon.
They sound like just grit, but you're saying they act as these miniature chemical labs floating in space.
That's the perfect way to describe it. Take molecular hydrogen, ATEROS, the most abundant molecule in the universe. It almost exclusively forms on the surface of these dust grains.
Why in the dust? Why not just in the gas?
Because it's incredibly inefficient in the gas phase. A dust grain acts like a meeting point. Two hydrogen atoms stick to the surface, they're able to move around, find each other, and bond. The grain absorbs the extra energy, and a stable H molecule floats off.
So without dust, you don't get the molecular clouds you need to form stars in the first place.
Your star formation would slow to a crawl, and dust also acts as the cloud's thermostat. It absorbs visible light from stars, heats up, and then radiates that energy away as infrared light.
Which cools the cloud down.
Exactly. And that cooling is essential. A gas cloud has to lose its heat pressure to be able to collapse under its own gravity and form a star. No dust, no cooling, no stars. It's a fundamental regulator of how galaxies evolve.
Okay, so let's put this all together. We have the fundamental fields, The gas and plasma, the dust, everything we can see or interact with. But all that baryonic matter is only what? Like 4.9% of the universe's total budget.
That's right. Now we have to talk about the invisible architecture that actually runs the show, according to the Lambda CDM model.
Let's run through those numbers again.
Dark energy is the big one, about 68.2%. Then you have dark matter at 26.8%. And everything else, everything we've talked about so far, is just that last 4.9%.
We live in a universe dominated by stuff we can't see.
Completely.
So dark matter, 27%. How do we know it's there if it doesn't interact with light at all?
Purely through its gravity.
Oh.
The classic evidence is galaxy rotation curves. The stars on the outer edges of galaxies are moving way too fast. The visible matter just doesn't have enough gravity to hold on to them.
So there has to be a massive invisible halo of something else providing that extra gravity.
An enormous halo of dark matter, yes. And it's not perfectly smooth. It clumps up around galaxies and along the filaments of the cosmic web.
And then there's the biggest mystery of all, dark energy. The 68% that's pushing the universe apart faster and faster.
Dark energy seems to be a property of space itself, a uniform, repulsive force. And unlike dark matter, its effects are strongest where there's the least amount of other stuff. In the great cosmic voids, where gravity is weak, dark energy completely takes over.
Beyond the dark stuff, though, space is also just flooded with radiation and particles we can detect, starting with the one that's literally everywhere.
The cosmic microwave background, the CMB. It's the leftover heat from the Big Bang, released about 380,000 years after it all started.
The first light.
The first light, yeah. Before that, the universe was an opaque plasma. But once it cooled down enough for atoms to form, the photons were set free.
And today, after billions of years of expansion, that light has been stretched into microwaves.
Correct. And every single cubic centimeter of space contains about 411 of these CMB photons. It's a near-perfect thermal bath at 2.725 Kelvin. And the tiny little temperature differences in the CMB are the seeds from which all galaxies grew.
And then in terms of particles, there are the neutrinos, the ghost particles.
The second most abundant particle, after photons. They barely interact with anything, so they stream through planets like they're not even there. But they carry information from the most violent events. That huge neutrino detection in 2023, around 220 peta-electron volts.
That's an incredible amount of energy.
It's colossal. And it probably points directly to a blazar or some other powerful cosmic accelerator billions of light years away.
We also have cosmic rays zipping around.
High-energy charged particles. They heat up the ISM, but more importantly, they create elements. When a cosmic ray hits a larger atom, it shatters it, a process called spallation. That's how we get most of the lithium, beryllium, and boron in the universe.
And finally, the last invisible component, magnetic fields.
Yes, vast, incredibly weak magnetic fields that stretch across galaxies. They're generated by the swirling plasma in the galaxy, a dynamo effect, and they help contain cosmic rays.
But the really mind-blowing idea is that some of these fields might be primordial.
Yes, recent 2025 simulations suggest that the magnetic fields in the intergalactic medium in the cosmic web might not come from galaxies at all. They might have been created in the Big Bang itself.
How weak are we talking here?
Billions of times weaker than a fridge magnet, maybe 0.2 nanogas. But if they've been around since the beginning, even that incredibly weak field could have helped shape where the first galaxies started to form.
So this is clearly a field of active discovery. What are the frontiers in 2025 telling us right now about this living vacuum?
Well, first, we're studying the voids to understand dark energy. NASA's Roman Space Telescope is going to map the precise shapes of tens of thousands of cosmic voids. Since dark energy drives their expansion, their shape tells us about its nature.
And we're seeing the IGM being actively changed as we watch.
Right, that cosmic Himalayas discovery from the Subaru telescope in June 2025. They found a tight cluster of 11 quasars, supermassive black holes, all lighting up at once, and their combined radiation is carving out huge bubbles and heating the gas in the IGM around them.
And we even got a physical sample, in a way, from another star system's empty space.
The interstellar comet 3I AT-LAS in December 2025, a phenomenal opportunity. These objects are time capsules, carrying the chemical signature of the interstellar cloud they were born in. It's like getting a direct message about the chemistry of another part of the galaxy.
To really get this, though, we have to understand the scale, how full space is versus how empty it is. Let's use particle collisions to try and grasp it.
It's the ultimate contrast. The average ISM is maybe 1 million particles per cubic meter. But in the deepest cosmic voids, that drops to about 0.01 particles per cubic meter,
Yeah.
1/100th of a particle.
Okay, so here's the statistic that just completely breaks my brain. In one of those voids, how long would a single hydrogen atom moving at a pretty normal speed have to travel before it hit another atom?
Approximately 1 trillion
A
years.
trillion years.
That's about 70 times the current age of the universe.
So for all practical purposes, the particles out there never, ever interact. They don't even know the others exist.
That's the paradox. Space isn't a container, it's a physical substance, a living vacuum. It's this incredible intersection of quantum fields, plasma, dust, radiation, and invisible forces that are shaping everything.
So the biggest secrets are written in the emptiness between the stars, not just in the stars themselves. Which leaves me with one final thought. If these primordial magnetic fields, billions of times weaker than a household magnet, could have been strong enough to help shape the first galaxies, what other incredibly subtle, seemingly negligible fields are out there, ones we haven't even measured yet, that might be quietly steering the ultimate fate of our universe?